In the next chapter, we're going to look at one of the important applications of the derivative, and that is finding the minimum and maximum values of a function. Oftentimes this is called optimization. You're wanting to either minimize something, or you want to maximize something, maximize the profit, let's say, or minimize the space. And so if you can get a function that gives you the different possibilities, then you can find the values that give you the maximum profit or the minimum space or whatever. Okay, so we're going to have to define a few things here, and this first section is going to introduce this concept in a very simple situation, and that is when you have a continuous function over a closed interval. In that case, it's fairly simple to find the absolute minimum and maximum values of the function over that interval. So let's start there by actually defining what I mean by the absolute minimum and maximum values of a function, because there's also relative minimum and maximum values. Okay, so a function f of x has an absolute minimum or maximum value at x equals c if for all x in the domain of the function, okay, it'll be a minimum if f of c is less than or equal to all the other possible values of the function over the entire domain. And then it has an absolute maximum if f of c is actually greater than or equal to all the values of the function over the entire domain. Okay, so sometimes these are called absolute, or sometimes it's called global. Global min and max, and this is compared to when you have relative min or max. We're going to look at that in the next video. And relative min or max is sometimes called a local min or max. Okay, so we're going to look at the global min or max, or absolute min or max here. And so I'm going to start with a really simple situation here to make a point. We're going to consider f of x is equal to x squared, so a parabola here, and I'm going to do it over the following domains. So normally we think of the domain for x squared as just being negative infinity to infinity. Okay, and so the function would look kind of like this. You'd have y equals x squared, and notice here that it would have a minimum value, and this would be a global minimum, okay, or an absolute minimum, right? And it would be at x equals 0. Okay, so at x equals 0 it has a global minimum value of 0, and all the other values are larger than that. Okay, notice this doesn't have a global maximum value, because from negative infinity to infinity it just keeps growing, okay, without bound, and so there's no maximum, but there is a minimum value. Okay, so now you can take a function though, and in different situations you're only interested in certain portions of the domain, and so you might restrict the domain of the function. So in this case I'm considering f of x equals x squared over the domain of just 0 to 2. And this is where 0 to 2 is a closed interval, so it includes 0 and 2. Right? So we'll say this is 0, and then at 2 we know that it's equal to 4. Right? And this is like just half of the parabola. Well, not even half of the parabola. It's just this piece of the parabola here. And then notice here, this is like a global max here, and this here is a global min. And so this would be the minimum value of the function over, an absolute minimum value of the function over this interval. This would be an absolute maximum value over that interval, over that closed interval. Okay, so now let's look at this. So we don't have a closed interval. Okay, we're going to include the 2, but we won't include the 0. Let's see what happens. So there's a open circle here, 1, 2, okay, and 2, and a closed circle here, and then this thing will go up like this, and then you can see that this, again, this will be a max in this case over the entire function, but here, is that a min? No, it's actually not. And so why is that? Well, this function does not take on a minimum value, because whatever value, first of all, this from 0 to 2, not including 0, it does not take on the value 0. Okay, so 0 would be a lower bound, right? All these values are going to be above, greater than 0, but 0 is not a value of the function. So I would need to pick something bigger than 0, but any number that I pick, even slightly more than 0, okay, that won't be the minimum, because you can always get a little closer to 0 and get another value. So these are kind of getting infinitely close to 0 and never quite touching it, but you can never state what the number right before 0 is, right? Because you can just get closer and closer and closer. So because of the way that infinity works and the real number system is, and the fact that between any two real numbers, you'll always have another real number between them. Between any two real numbers, there's an infinite number of real numbers between them. It's just how the real number system works. So this does not have a min, okay? But it does have a max. So here, this is an open interval. Again, this is a completely open interval, and so it's open at 1, and it's open at 4, and then it takes on all the values between that. So notice here, there's no min or max here, okay? Because you have the same issue here going on with 0, and then you also have the same issue going here. You can get closer and closer to 4, but you're never going to reach 4, and there's no largest number, right? There's no largest number of the function that's going to be bigger than all of the other values of the function on this interval. Okay, so you can see that including the endpoints is important. So when you have a closed interval here, it took on the min and the max values. Here, this didn't take on a min, and the problem was we didn't include the 0. In here, this didn't take a min or a maximum value, and we didn't include either of those. So the idea of looking at the function on a closed interval is important, and what you get here is a theorem called the extreme value theorem. Sort of like the intermediate value theorem, and I think it's probably based on the intermediate value theorem. But basically it says if a function is continuous on a closed interval, AB, so it has to be continuous, then f is going to attain both an absolute min and an absolute maximum on the closed interval. Okay, that is, there's going to be two values, we can call them x sub 1, x sub 2, in AB, with x sub 1 being little m, x sub 2 being big M, such that all the values of the function are going to be trapped in between those two values. And these are values of the function. Okay? And so, basically, if you have a continuous function on a closed interval, it will achieve both a minimum value and a maximum value at somewhere in that interval. Okay, so here's a cubic equation, and we know the cubic polynomials are continuous, no problem there. And here is a closed interval. So this will contain both a minimum and a maximum value. Okay. And so let's look at this function. I'm going to graph it here. So x cubed minus 3x, try it again, x cubed minus 3x squared minus 2x plus 3. And then I guess we'll do this on a standard window. Oops. And so it looks like we have a cubic polynomial that goes up, down, and back up. So it's kind of, it looks like this. It goes up, down, and back up. Okay? And let's look at where 3 and negative 3 is. So I'm going to hit the value function, and I'll do negative 3. And negative 3 is like 45, right? So it's like way down here. There's a point where this is like negative 3, and this point here is like negative 3, 45. And then positive 3. So if I put in a positive 3, I get negative 3. So here at a positive 3, this point here is like 3, negative 3. Okay? And so, but this is actually up here somewhere. This is actually not. It's actually like right around here. So this would be like positive 3. Okay? So you really have like this portion of the graph. Okay? And it's going to stop here, and so this is what you're considering. Okay? So notice it contains an absolute minimum right here, and it's at the end point. Okay, now this other endpoint is not an absolute maximum, so the absolute maximum is actually up here. Okay, so this is the largest value. Now, over the whole domain of the function, that wouldn't be the maximum, because you just go over a little bit, and then you're going to be way up here. But from negative 3 to 3, the function takes on a minimum value and a maximum value. Okay? And they won't necessarily occur at the endpoints. Okay? So if this function, let's say, started up over here, this would have been the maximum, and then that would have been the minimum over there, right? But because it started way down here, this is the minimum. So these sort of points where you got like a peak and a valley, those are called relative min and maximums, and we're going to look at those in the next video. So sometimes they're called local min and maximums. So for all the values around those points, for those values around the points, they're bigger or smaller than the other values around the point, but not over the entire function. Okay? So, so we see that the minimum, the absolute minimum and maximums over a closed interval will either occur at the endpoints or at these like turnaround points, these relative min and maximums. Okay. So let's look at this one here. So this one is okay, sine of x on the interval pi over 6 to 2 pi over 3. So let's see if we can do this. I could probably graph this here, right? If this was 2 pi and this was pi, right? And this was pi over 2, right? This would be like pi over 6, right? And then at pi over 6, sine is like square root of 3. If this is 1 and this is negative 1, this would be like square root of 3 over 2. And that's kind of where this function is starting, pi over 6. Right? And it's going, it's like this, dot, 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 but then it starts here, it goes up, okay? And then it's not even going to this pi, right? It's going to 2 pi over 3, which is like, the 2 pi over 3. Oh, and pi over 6 actually, sorry about this. The pi over 6 is actually 1/2. I shouldn't have erased that though. I mean, square root of 3 over 2. So the pi over 6 is actually like 1/2. And then the 2 pi over 3 is actually the square root of 3 over 2. So you got 2 pi over 3, and this is the square root of 3 over 2. And then you have, this is pi over 6, and you have 1/2. And you just have this portion of the graph, right? Okay. And maybe I should have just done the whole graph so you could see this. You know, I didn't do very good. It would look kind of like this, right? This is what it would look like, and then I have like this portion of the graph. Okay, so the minimum for that on this closed interval would be right here. That's the global minimum. Now this is not the global maximum. The global maximum is going to be right here, and it'll be a maximum of 1, and it's going to occur at x equals pi over 2. And I just know that naturally because I know the graph of sine. Okay? Notice that this is also each of those peaks and the valleys down here. These are relative min and maximums. Okay? So in this case, I couldn't tell you. It looks like this relative min is at 0, but if you look at the graph, it's actually not. It's actually over a little bit. Okay? And then this one here, I'm not quite sure where that's at. So with this cubic equation, I can't necessarily tell you where these relative min or maximums are going to occur. But in the next video, we are going to find out where they occur and how to find those places. Okay? And what we're going to basically find is when the derivative is equal to 0 is what we're going to find, right? Because you got these horizontal tangent lines. Again, right here, these are when the derivative is equal to 0. So, there you go. If you have a continuous function on a closed interval, somewhere on that closed interval, you're going to have an absolute minimum and an absolute maximum over that interval. Okay, but it is important that you have those conditions met. Okay, and those conditions are, it needs to be continuous on AB, right? And AB is a closed interval. So you have to have those in order to get the absolute minimum and maximum values. So let's show a couple examples where this actually fails. Okay. So this one here, we have it's a parabola here, and it is this is actually one that's moved over 3 over to the positive side 3, and then it's moved up 2, right? So it'd be like right here, and it's upside down, so it would be like this. So it would be something like this, and not sure where that's at, but it doesn't include this point. And then it goes to 5, and at 5, this is like 4, and then at 5, it's actually going to be like down at -2. And it does include the 5, okay? So this would be 5, -2. Okay, and then this is like 0, 9, and this would be like -7. Okay, so here's an example where we don't have a closed interval. Now it does contain a max here at 3. So 3, 2 is the vertex. And so this is a global max over this interval. So it does contain the maximum value, but does it contain the minimum value? And it doesn't here, because this point over here, this is not a min, right? This is an open circle, so it doesn't have an absolute min. It only has an absolute max in this case. Now, it doesn't mean that it couldn't have an absolute min or max. So if I did like from 2 to 5, if I did like, well, not 2 to 5, yeah, if I did 2 to 5 and 2 was an open circle, 5 would be a min in that case. This would be an absolute min and that would be an absolute max. So, in other words, 2 to 5, this would contains min and max. Okay. So it doesn't mean that it does not have an absolute min or max. It just isn't guaranteed to have an absolute min or max. Okay. If it's a closed interval, though, it would be guaranteed. If that were closed, you would be filling in that dot, and that would be the minimum value. Okay. Does that make sense? So now this function, f of x, and let me write it down here, because I got it all messy here. This is sine of x over x. And if you remember, this is the one where at 0, this thing is not defined. But if you take the limit as x goes to 0 of sine of x over x, this is that special limit that is equal to 1. This is the limit that I proved back in the previous chapter. And so this here, let's say this is negative 3 pi over 2, and then you have 3 pi over 2. And what you actually get is you get something that looks like this, and it contains these endpoints. But there's an open circle here. It's actually not equal to... It's not defined at 0, okay? So so in this case, this is a closed interval. So the problem with this one is it's not a closed interval. Okay? This one, it is a closed interval. The problem with this is it's not continuous. And so you see that these are actually, and these are going to be the same value. I think they're equal to like 1.5 or negative 1.5, negative 1.5. Actually, I should do 3 pi over 2, negative 1.5. And let me just make sure I'm giving you the right value. I'm going to graph that. So I'm going to do, sine of x divided by x. And I want to get a good window of this. So let me do negative 2 pi to pi. And then I'll do negative 2 to 2. Oops, it's offset a little bit. Oh, I should have done negative 2 pi to sorry, I should have done negative 2 pi to 2 pi is what I meant to do. Ooh. There we go. So just looking at it, it would seem that is a maximum value there. Okay. So if let me look here. Second calc, and I'm going to do value, and I'll do negative 3 pi over 2. And oh, this is not 1.5. I'm not sure what I was thinking. It's like negative, you could probably calculate it exactly, but like negative 0.12. And then negative 3 pi over 2 is also negative 212. Okay, so these are the minimum values. Okay, but the maximum value, this is not a max. Okay, because it doesn't take on 1. It'll get infinitely close to 1 on either side, but it doesn't take on the value of 1. Okay, and so the problem with this one then is it fails to be continuous. So if a function, though, is continuous on a closed interval, there will be a min and a maximum value over that interval. And they're going to occur either at the endpoints of the interval or where the graph turns around, where that relative min or max occurs. So in the next video, we are going to look at those relative min and max.